This video is on functions, so this is basically an extension and a second part to the functions video that I made in year 1, so please make sure you understand all the content from that. So a word that comes up a lot when we talk about functions is mapping. And mapping is basically when we transform one set of numbers into another set of numbers. We convert an input into an output, and we do this by mapping. It sounds like what a function is, and it basically is, but technically it's not always, which we'll discuss in a sec. So there are 3 mapping examples that you need to be aware of. The first is a one-to-one mapping. And this is where each input gives out one unique output. And you can see this with this diagram here, where each input gives out its own unique output and no 2 inputs give out the same one output. And an example of this is a linear graph, where every single x value gives out its own unique y value. The second type of mapping is many-to-one mapping. And this is when multiple inputs can go to the same one output. And you can see this in this diagram here, when these 2 inputs can go to this exact same one output here. So an example of this is a quadratic, such as y is equal to x squared. If we put a line here and say this is when y is equal to 4, and we can see that there are 2 x values, 2 points of intersection, that give out y is equal to 4, and this is because 2, so it's y is equal to x squared, 2 squared is equal to 4, but also minus 2 squared is equal to 4. So this is an example of a many-to-one mapping, where 2 x values can give out the same y value. And then the third type of mapping is a one-to-many mapping. And this is where one input can give out multiple different outputs. You can see this with an example where this one input can give out 2 different possible outputs. An example of this is y is equal to plus or minus root x, where if we draw a straight line like this, and we say that this is where x is equal to 4, we can see that there are 2 points of intersection, and this is because plus or minus root 4 is of course equal to plus or minus 2, because there is the plus or minus root when you square root 4. It could be 2 or it could be negative 2, so it could be 2 here or it could be negative 2 here. One-to-many mappings are actually quite rare, but they do exist. So these are the 3 types of mapping, but mapping is not the same as a function. A mapping is a function if all inputs give out exactly one output. So what this boils down to is a mapping is a function if, and then 2 conditions need to be met. The first is that each input gives out only one output, and then the second condition is that every input has to give out an output. So let's focus on condition 1 first, that each input gives out only one output. And let's consider the 3 types of mapping. So let's start with a one-to-one mapping, and this is fine because each input gives out only one output. There is no input that gives out 2 outputs, it's always only one output that is given out. For the same reason, a many-to-one mapping is okay as well, is that each input only gives out one output. 2 inputs can give out the same output, but that doesn't matter as long as each input only gives out one output and doesn't split into 2 different outputs. And for that reason, a one-to-many mapping is not a function, because one input can give out 2 different outputs. So these 2 are functions, as each input gives out only one output, but this here, a one-to-many mapping, this is not a function, as each input gives out multiple outputs and not just one output. So for something like plus or minus root x, we have to alter the mapping in order to turn it into a function. And we'll see how to do that in a sec. The second condition, and we'll discuss this in a sec, but if it's the case that some inputs don't give out an output at all, it's not a function. And this is surprisingly common. So for example, if we had something like y is equal to 1 over x, and if we said that x is equal to 0, we're doing 1 divided by 0, which we can't do. So therefore, this is not a function because we cannot divide by 0, so there's no output. So we have to alter it slightly, and we'll see how to do that in a sec. So I think the easiest way to explain this is to go through some equations and discuss if they're a function or not. So here we have the equation y is equal to x squared minus x minus 2. And I want to ask, is this a function? Okay, so firstly, we have this comma here, and then we have this. This comma signals that anything after it is the domain. We discussed what this is in the first functions video, but the domain is the set of possible inputs, and then the range is a set of possible outputs. And this here, this R means the domain is real numbers. Now, in exams and in the book, this is an R, but it looks a bit different to this, but I have no artistic ability at all, so I'm just going to do it like this. It looks pretty much the same here. And to be honest, you can just ignore this. What this R actually means is that the domain is real numbers and not imaginary numbers, which is something you discuss if you do further maths. So to be honest, again, you can just ignore it. It doesn't really impact the question. It doesn't really matter. So the question again, is this a function? Well, if we look at the graph here, we can see that it is a many to one mapping, where multiple x values can give the same y value, but most importantly, every single x value gives one y value. That's the most important thing, and we talked about in the intro that a many to one mapping therefore is fine. So the first condition is met because every single x value only gives out one y value. And for the second condition, every input gives out an output. Every single x value will give out a y value. There's no kind of like x value that doesn't work. Every single x value gives out a y value. So this is fine as well. This condition is met too. So therefore, yes, this is a function as it satisfies the two conditions for when a mapping is a function. So here's another equation where y is equal to plus or minus root x. And the question is this a function? Well, if we look at the graph, we can see that this is a one-to-many mapping, as one x value gives out multiple y values, the plus or minus square root. So this is a one-to-many mapping. And therefore, as we talked about before, this breaks the first condition, as each input does not only give out one output, it gives out two. So therefore, this is not a function. So now the question is, how can we make this a function? Well, what we can do is we can say that rather the mapping being y is equal to plus or minus root x, we can say that it is just positive root x, which of course we can just write as root x. Of course we could do this for the negative instead, but let's just do it for the positive. And what this will do is this will get rid of this section of the graph. It will just get rid of it because it cannot equal the negative square root now. And now this is a one-to-one mapping because each x value now only gives out one y value. So therefore this condition here is now completed. Each input now only gives out one output instead of before where it gives out two. However, if we look at the second condition, that every input gives out an output, over here we can see that we have no graph for any of the negative x values, and this is because you cannot square root a negative number. You cannot do the square root of -1, it just doesn't exist. It doesn't give out an output. So we have broken the second condition that every input gives out an output, because for all of the negative values, it doesn't give out an output. So this is not a function either. So the question is now, how do we make this a function? Well, what we have to do is alter the domain. We have to do, so we're going to put a comma to show that we're now introducing the domain, and we have to say that x has to be bigger than or equal to 0. And what this basically does is this basically just gets rid of this section of the graph. We're basically saying you can only use this mapping if x is bigger than or equal to 0. And this is completely fine to do, because now we've got rid of all these negative values, and now we have satisfied the second condition. Every input now gives out an output, because we don't consider the negative values for this mapping. We just say that it doesn't work. And therefore this is now a function, because it is satisfied both of the conditions of the equation. And we have done this by adjusting the domain. So the values that break the second condition here are no longer not included. Now this x is also real numbers, and you could also write this over here as well and say that x, clarify, that x is real numbers. If you really wanted to, it could also be written here, but as I said before, it doesn't really matter too much. I wouldn't write it. And sometimes you will see that this domain here could be smaller than this. It could be something like for example, x is between 1 and 5, and this will still be a function, because this still satisfies both of the conditions in this domain. Every input still gives out an output in this domain. It's just a smaller segment of the domain that we used before. But the biggest domain that you can use is that x is bigger than or equal to 0. The only thing that you can't do with the domain is say that x can be negative values, because x cannot be negative values, because therefore the function would no longer exist, as every input would no longer give out an output. So here's one more equation where y is equal to 1 over x, where x is real numbers. And the question is this a function? So let's consider the first condition, that each input gives out only one output. So this is a 1 to 1 mapping, where every x input gives a different y output. So that's fine, as we said before, that satisfies this first condition here. However, for the second condition, there is one x value that doesn't give out a y value, and we've mentioned this already. This is when x is equal to 0, because this will be y is equal to 1 over 0, and we can't divide by 0, we can't do it. So therefore this is not a function, because it breaks this condition here that every input gives out an output, and there is one input that does not give out an output, and that's when x is equal to 0. So the question I'm going to ask again is, how do we make this a function? Well, again, we alter the domain. So this is still fine, y is equal to 1 over x, and this works for every single value except for 0. So we just say the domain, again we do the comma to introduce the domain, we just say that the domain is everything except for when x is equal to 0. We just don't include when x is equal to 0, because it cannot equal it. And now this satisfies the second condition, and therefore this is now a function. So we have just said that x is not equal to 0, we just don't include it in the function, and therefore this does become a function. So to make something a function, you can alter the domain, so all the x values in the domain will have exactly one y output. So they could ask you for a function to find the range for a given domain. Just a reminder that the domain is the set of possible inputs. So these are the x values, and this is given by this here, so it could be between 0 and 5, and the range is the set of possible outputs. So these are the kind of y values. So this is the domain, and we need to find the range. And for this example, as it's linear, this is very easy. The smallest value in the domain will be the smallest value in the range, and vice versa for the largest value. So this is the smallest value for the domain, and this will be the smallest value for the range. So to calculate this, it would be f of 0 is equal to 3 over 2 of 0 minus 6, and this will just be equal to minus 6. So this is the smallest value that you could get out, so therefore this is the smallest value in the range. And then the biggest value is this here when you plug it into here. So this is f of 5, which is equal to 3 over 2, 5 minus 6, which is equal to 15 over 2 minus 6, which is equal to 3 over 2. So the range of the function is between this and this, so it's minus 6 as the smallest number, and it could also be equal to minus 6 because we have the equals inequality here as well. F of x and then 3 over 2 is the biggest value. So here's another example. So this terminology here you might not have seen before. This just means f of x is equal to, and then whatever is this here. It's not as scary as it looks, so you can just treat this as f of x. So in this example, as x is in the denominator, it's inversely proportional, and it's actually the opposite to last time. The biggest value in the domain will give the smallest value in the range, and vice versa. So the smallest value in the range will be when x is biggest, because x is in the denominator. So this is going to be f of 7. You can just write it like this, even though it's written like this, it doesn't make a difference. So f of 7, the biggest value in the domain, is equal to 3, 7 plus 4 under 5, and if you put that into a calculator, that is equal to 1 over 5. So that is the smallest value in the range, and then the biggest is when we plug in 1. So this is f of 1, and this is equal to 3 of 1 plus 4 under 5, which if you put into a calculator is equal to 5 over 7. So this is the smallest value in the range, and this is the biggest, so it's the smallest value is 1 over 5, and then the range lies between this. You can just write this as f of x, it doesn't really matter, and the biggest value of the range is 5 over 7. So the range, all of the outputs lie between 1 over 5 and 5 over 7, and we don't put the equals inequality here, bigger than or equal to, because this is not the case for the domain. We don't have this here, so we just write it like this, and that's the answer. So here's another example. Now this is a bit of a different example, as even though there is no set domain beyond just saying that x is equal to real numbers, remember you can just ignore this, it doesn't really matter, there is a set range, and this is because of the way this function works. If we draw the graph, remember how to draw the graph of an exponential, it looks like this here, where we have a y-intercept at 1, and this is the graph of y is equal to g of x, and it has an asymptote at y is equal to 0. So therefore the range is going to be when g of x is bigger than 0, because remember that this graph can never go below this line here, the asymptote. There is no way that this graph can go below this, but remember that there's no equals to here because this is an asymptote. It never actually touches this line. There is no way that e to the power of x can actually equal 0. There is no value of x in which that's the case. There's no upper value for the range here because this just keeps going forever and ever and ever, but there's a lower value. It has to be bigger than 0, and that's the final answer. Very finally, sorry for the surprisingly long video, we have something called a piecewise function. A piecewise function is where you have, in this case, two different domains in which two different functions are used for those inputs. So here's an example of a question on this. So for part A, we need to find the values of f1, f3 and f5. So f1 is going to be, so the x value is 1, and we need to see what domain 1 lies in, and 1 is less than 3. It doesn't lie in this domain, so therefore we use this function. So f1 is equal to, and then we plug x into here, so it's going to be 1 plus 2, and this is equal to 3, so f1 is equal to 3. f3 is going to be equal to, and then what domain it lies in this one, because x is bigger than or equal to 3, so it lies in this domain where x is equal to 3, so we use this function. So it's going to be x squared plus 4, so it's going to be 3 squared plus 4, which is equal to 9 plus 4, which is equal to 13. So f of 3 is equal to 13, and then f5 is equal to, and this also lies in this domain because it's bigger than 3 or bigger than or equal to 3. So we use this function. So f of 5 is 5 squared plus 4, which is equal to 25 plus 4, which is equal to 29. So f of 5 is equal to 29. So for part B, we have to solve the equation f of x is equal to 20. And in order to solve this, we have to consider the two functions individually, solve to get a value of x, and then we have to consider if these values of x that we give out lie in the domain. So let's start with x plus 2. So if f of x is equal to x plus 2, it would be x plus 2 is equal to 20. So therefore it would be x is equal to 18. So x is equal to 18 for this function, but the function for the domain for this function is when x is less than 3, and 18 is not less than 3, so therefore x cannot be equal to 18 as it doesn't lie in the domain for this function to be used. The other function is x squared plus 4, and this is equal to 20, so this is going to be x squared is equal to 16, so this is going to be x is equal to plus or minus the square root of 16, which is 4, and this is for the domain when x is bigger than or equal to 3, so therefore x cannot be equal to minus 4 because this isn't bigger or equal to 3, but x can be equal to 4 because this does lie in the domain when x is bigger than or equal to 3. So there is one solution when x is equal to 4, and that's the final answer. So for part C, we need to sketch the graph of f of x, and this is the same as before. We need to individually consider or sketch the two functions for this domain here. So let's start with x plus 2. So just focus on this for now, and I'm just going to sketch the graph of x plus 2 in general. So this is the graph of x plus 2, but we only want it in this domain here where x is less than 3. So if we say 3 is about here, we don't include this region here because this is bigger than 3. We only want this region here. So only this is going to be included in the final answer. And at the end of the domain, we put a circle here, and we leave it blank if it can't be equal to the end of the domain, but we shade it in if it can be equal to the end of the domain. But as x cannot be equal to 3, it has to be less than it. There's no like equal inequality sign here. We leave it blank like this, and we don't shade it. We just leave it blank like this, where we have a y-intercept at 2 and a root at minus 2, and then what we do is we focus on the other part where x squared plus 4, and then we sketch this. So this is going to look something like this, and this, like that. And then what we do is we only want this when x is bigger than or equal to 3. So this is here, so we only include this region here, and we're not interested in this region. And we do another circle like this, and this time we do shade this in because we've got this equal inequality like this, so it could be equal to 3 here. And then this is the final answer. This is the graph y is equal to f of x, where the red part is the final answer and then the grey part is just the working that we've done to figure it out.